Okay, we're going to spend a moment here refreshing on the unit circle. So if I've got an angle theta and I want to know its sine and cosine, tap right into the point that theta's angle intersects on the unit circle. Okay, so the sine component is the y and cosine is the x, and then I can build all the others from the x and the y, provided this is a unit circle. Okay, if you think about this angle theta, and we've talked about how you're allowed to wrap around, cycle all the way around and come back, and we have a coterminal angle. It's how much larger is this coterminal angle? Well, once we got to that endpoint, we had to go another full rotation to get back to it, and that's a 2 pi, right? So whatever this theta angle is to begin with, every 2 pi, if I start from there, I come back there. So every multiple of 2 pi beyond theta is going to bring us right back there. So let's look at some results that. Okay, so what we've really just said is that if I take some angle to begin with that we call theta, and I add some multiple of 2 pi, then I'm going to take right back to that same point. And we're just going to say this is true for k equal to 1, 2, 3, 4. So as long as k is an integer, then we're going to be able to get right back to this point. And so that's going to help us with finding exact values of the sine and the cosine for any angle that can be restructured to be some angle theta plus some multiple 2 pi times some integer k. All right, let's put that to use here. Okay, the name we give that kind of a function is periodic if it keeps coming back to the same place. So in general, we're going to say it's periodic if we've got some number such that whenever theta is in the domain of f, and so is theta plus p, and we can discover that theta plus p is the same as theta for that function. In our case, the function or the operation is the sine and the cosine. So if there is a number, then the smallest value is the fundamental period. So that's just saying the first wrap. So if I go up by theta and then I do this, then that is going to be the fundamental period, okay, the smallest value. We can keep wrapping as much as we want. Okay, so here are the properties that are developed because of this. We have the period for the sine we've discovered is 2 pi, because after you get the theta, if you do a 2 pi, you get back to it. So that's ends up being the period because it's the smallest value. Of course, 4 pi would take us back there as well, but 2 pi is the smallest. So that would be the fundamental period based on that discussion. And for the sine and the cosine, we notice both are 2 pi. Interestingly, when we get to the tangent, if you think about the quadrants, okay, so for the tangent, whatever I get in quadrant 1 is going to be an identical result for what I get in quadrant 2. And the reason for that is that in quadrant 1, let me change this pen here. Okay, so in quadrant 1, we have plus, plus, right? So for a y over x, we're going to get plus, plus. And then if I go over to this side, we have negative, negative. And so y over x is a negative divided by a negative. So remember that if I divide a negative by a negative, I get back a positive. And the y and the x are going to have the same absolute values. So the y over x that I make here has a partner over here. And that's why the period is only pi. It's halfway around. So if I go halfway around and keep going halfway around, I get back to the same tangent. So the fundamental period for tangent is just pi, not 2 pi. And then the ones that are related here are going to have the same fundamental periods. So since the cotangent goes with the tangent, its fundamental period is pi. But since the secant goes with the cosine, we'll keep the 2 pi. And since the cosecant goes with the sine, we keep the 2 pi. Okay, so that's what we mean by periodic. Okay, so here's how we're going to put this to use for us. If I come over here and I look at sine function, I know that's periodic over 2 pi. So every time I go 2 pi, I'm back to where I was. So if we rethink 17 pi over 4 as 16 pi over 4 plus 1 more pi over 4, then of course 16 pi over 4 is 4 pi plus pi over 4. Okay, so now we've got this multiple of our period and our start point here. So the theta part would be pi over 4. So remember we did pi. So we had theta plus 2 pi times some integer k, right? So in this specific case, what we're really looking at is a sine. Pi over 4 is our theta. And then I'm just kind of spinning my wheels here with the 2 pi. In this case, k is 2 because we have 4 pi. So I really only need to concern myself with what's the sine of pi over 4. And the sine of pi over 4 is equal to, from our unit circle, the square root of 2 over 2 is the exact value. Okay, so how about the cosine of 5 pi? This one's a little easier here because if we go, we know that 4 pi is going to take us twice around, right? There's 2 pi, 3, 4 pi. And now I've only got 1 pi left to go. So I can rethink this as the cosine of pi plus 4 pi. And that's equal to the cosine of pi. Okay, and we know that from the unit circle again that the cosine of pi is -1. All right, for tangent, now remember that the period here is just pi. So this was our period for both cosine and sine. But the period for the tangent is just pi, so we're going to have to think about this a little differently. So if I have 5 pi over 4, then I've gone 1 1/4 pi's, right? Because that's 5 pi over 4, 5 over 4. So let's do the 1 pi, and that puts us here, because remember pi is just half the way around. And then from there, I have to do a pi over 4. So we're going to say pi over 4 plus pi. And so pi over 4 more from there is going to take us, so this is like, from our unit circle, we can see that's 5 pi over 4. So the tangent is going to be the same as the tangent of pi over 4. And on our unit circle, the tangent of pi over 4 is equal to 1. Okay, so this is a good example to discuss, just real quick, what's going on there. Oops. Okay, that's what I need is my little picture here. Okay. So if I just go pi over 4, we already knew that pi over 4 is halfway here, right? And that's the square root of 2 over 2 for both x and y. And so the tangent pi over 4 is equal to this number divided by this number. They're both positive, and they're both the same. So you divide the number by itself and you get a 1. And since they're both positive, it's 1. Now this is 5 pi over 4 over here. And the xy coordinates are negative square root of 2 over 2 and negative square root of 2 over 2. So we've just shown that that one period of a pi rotation takes me into the other quadrant, but the tangent is the same. Because it's equal to the same negative value divided by the same. So divide any number by itself and we get 1, divide a negative by a negative and we get a positive. So notice that we end up with the same answer. So that's why the tangent has a shorter period than the sine and cosine. All right, so let's continue on here. For this one here, this problem C that we looked at, that's the only one you actually could have read directly off the unit circle because 5 pi over 4 is actually within one rotation and appears. But this just shows you that once you go 180 degrees or pi radians, you're going to hit the same tangent result as you do in the other quadrant. So this quadrant has all common tangents as this quadrant, and this quadrant has common tangents in this quadrant. And then the y-axis, so the tangent is going to be 0, or I'm sorry, it's going to be undefined here, and it's going to be 0 here and here. Okay, so let's move on. These are just some things you can kind of glean off of this if you think about it. Okay, so the sine and the cosecant have this quality. If I take a sine or a cosecant above the x-axis in either quadrant 1 or 2, then we'll get a positive result. And then if I take the sine or cosecant below the x-axis, I'll get a negative. I wouldn't bother memorizing this because it's basically built into the signage of each of the quadrants and the parts from the point that you need to use. But if you want to study that for yourself and just understand why it's so. Okay, so we're going to do a little thought problem here. So if the sine of theta is less than 0, so that means y is negative. I'm just going to mark that up as negative, so y negative. And the cosine is greater than 0, that means that x is positive. What quadrant is the angle in? Okay, so if you go forward for x and down for y, that puts it in quadrant 4, right? So this is where x is positive, and then down below that is where x is negative. So since we're talking about plus minus situation for xy, that puts us there. All right, so this carries over from the notion that cosecant of theta is equal to 1 over y, and the sine of theta is equal to y. So 1 over y is the same as 1 over sine of theta. And the cotangent, if I take let's just take 1 over and then the tangent is y over x, right? So this forces me to flip that and make it x over y. And so that's why the cotangent can be described as 1 over the tangent of theta. Okay. Another thing that we can look at is, since the tangent of theta equals y over x, and y is the result for the sine of theta, and x is the result for the cosine of theta, we see an identity that tangent of theta equates to sine theta over cosine theta. And the cotangent, in a like manner, will result from a cosine of theta over sine of theta, because that's x over y. Okay, so these are pretty fundamental, and but they're useful. All right. So now they're going to give us some results here to work with, and we know that y is equal to the square root of 2 over 2, and then x is equal to 5 times the square root of 2 over 2. Okay, so that leaves for us to find, we've got the sine and cosine, so here's what we need. We need the tangent, cotangent, secant, cosecant. Okay, so let's start with the tangent. Tangent theta equals y over x. So that's going to be equal to the square root of 2 over 2 divided by 5 times the square root of 2 over 2. So remember, flip and multiply here, and we're going to end up with a square root of 2 over 2 times 2 above 5 times the square root of 2. And I get to whittle this down a little bit. My 2's are going to divide out. My square root of 2's are going to divide out. And all I have left up here is a 1, and all I have left down here is the 5. So it must be equal to 1/5. Okay, so let's go ahead, and that gives us the cotangent for free, since it's the reciprocal of the tangent. So the cotangent is going to be 5 over 1, or 5. And remember that our secant goes along with the cosine. And so we're just going to say this is 1 over the cosine theta, which we have. So that's 1 over 5 times the square root of 2 over 2. And so if we just flip that, I didn't have to go to all that trouble, I know. But we do have to go to the trouble of rationalizing the denominator. So we'll multiply it by a square root of 2 divided by a square root of 2. So that's going to give us 2 times the square root of 2 over 5 times 2. And so that 2 will divide out, and this will just reduce to a square root of 2 over 5. Okay, so I'm hurting for a little room here. So for the last one, let's see. We'll do away with the tangent and the cotangent. All right, so now I need to find last one is the cosecant, and that's 1 over the sign. So let's flip that sign. And then let's rationalize the denominator. It's going to be 2 times the square root of 2 over square root of 2 times the square root of 2, which is 2. And then, of course, this simplifies. To just the square root of 2.